In the second part of elements of group 16, 17 and 18, we are going to study about their chemical properties, their reactivity towards metals, oxygen and halogen. The first chemical property which we are going to study is oxidation state. Group 16 elements. We know the general electronic configuration of group 16 elements is Ns2Np4. Hence, group 16 elements can attain a noble gas electronic configuration if they accept 2 electrons. If they accept 2 electrons, then the configuration Np4 will become Np6, which is the electronic configuration of noble gas. By sharing 2 electrons, they form a covalent bond. Hence, they can share or gain 2 electrons. And this is the reason that elements of group 16 exhibit oxidation state of -2 and +2. How would you define oxidation state? It is the number of electrons gained or lost to form a bond, and its sign is the indication of ionic charge on the element. We are aware that oxygen is the most electronegative element after fluorine. So the difference between the electronegativities of oxygen and other metals is very high. When oxygen and metal combines, it forms metal oxide, and here the oxygen attains the O2- form. 2- means it is accepting 2 electrons, and hence the minus sign, and the oxidation state is -2. Electronegativity of group 16 element decreases down the group in the periodic table. Elements like sulfur, tellurium, selenium react with more electronegative element of group 1, 2 or lanthanides to form sulfides, selenides and tellurides. These compounds which are formed by these elements are most stable. These compounds formed here can be denoted as S2-, Se2- and Te2-. So their oxidation state will be -2. So these were the examples of group 16 elements wherein they accept electrons and get that negative oxidation state. Now we shall study the examples of positive oxidation states of group 16 elements. Group 16 elements also share their electrons with other elements to form 2 covalent bonds. Some examples are H2O, that is water, F2O, Cl2O, H2S and SCl2. If you observe the table here, oxygen and sulfur has only S and P electrons, whereas selenium, tellurium and polonium have D electrons. We know that when the filling of D shell takes place, the atom becomes smaller and the electrons are packed very tightly. Hence, it is difficult to get the highest oxidation state of +6. However, sulfur and tellurium can attain oxidation state of 4 and 6, which is considered to be more stable than +2 oxidation state. We know that oxygen is the most electronegative element in group 16 elements, and it shows the common oxidation state of -2. However, it differs in case of OF2, where the oxidation state is +2, and also in case of peroxides like hydrogen peroxide and sodium peroxide. These are the examples of it. Now we move on to study the oxidation state of group 17 elements, which are also called as halogens. The general electronic configuration of group 17 element is Ns2Np5. So in order to attain the noble gas configuration, it has to attain or accept 1 electron to form E- ions, or has to share 1 electron to form a covalent bond. All halogens exhibit -1 oxidation state because they accept 1 electron and attain the noble gas configuration. Chlorine, bromine and iodine also exhibit oxidation state of +1, +3 +5 and +7. And the reason for this variable oxidation state is because these elements are less electronegative when compared with fluorine and also have empty d orbitals in the valence shell. The oxidation state of +4 and +6 is observed in oxides and oxoacids of chlorine and bromine. Fluorine exhibits -1 oxidation state because it does not have vacant d orbitals in the valence shell. Next are the oxidation states of group 18 elements, which are also called as the noble gases. Group 18 elements have a stable electronic configuration of Ns2Np6. Hence, they have no tendency to either gain or lose electrons, and that is why their valency is 0. And also they exist as monoatomic gases. Mono means 1. Xenon has a larger atomic size and lower ionization enthalpy when compared to other elements like helium, neon, argon and krypton. And that's the reason xenon exhibits higher oxidation states. The outermost shell of group 18 elements is the d orbital. The pair electrons which are present in the valence shell can be made unpaired by promoting it to the vacant d orbitals. So the electrons which are now unpaired can be paired with atoms of oxygen, fluorine and covalent compounds. Now we move on to study the chemical reactivity towards hydrogen. The elements of group 16 react with hydrogen to form hydrides of the type H2E, where E stands for elements like oxygen, sulfur, selenium, tellurium and polonium. Some examples of hydrides of group 16 elements are H2O, that is water, H2S, that is hydrogen sulfide, H2Se, that is hydrogen selenide, H2Te, that is hydrogen telluride, H2PO, that is polonium hydride. Out of this hydrides form, H2O, which is water, is odorless and colorless liquid, whereas H2S, H2Se, H2Te, H2PO are colorless, bad smelling and poisonous gases. All the hydrides formed have an angular structure and sp3 hybridization around the E atom, that is the element. Element will be placed in the center, so E is the central atom. The hydrides of group 16 elements are weakly acidic. The acidic nature increases while the thermal stability decreases as we move from H2O to H2Te. Thermal stability is the heat resistance of that particular hydride formed. The decrease in thermal stability is due to the decrease in the bond dissociation enthalpy of the He bond down the group. All the hydrides except water have reducing property, with H2Te having the highest reducing property, followed by H2Se and then H2S. Reducing property is the tendency of an element to lose electron. Next are group 17 elements. The elements of group 17 react with hydrogen to form hydrogen halides. So, hydrogen reacts with an halide which is represented by X to give hydrogen halide. Here X could be fluorine, chlorine, bromine and iodine. The acidic strength of hydrogen halides increase in the following order. Thermal stability of hydrogen halides decrease in the following order, and this is due to decrease in the bond dissociation enthalpy of HX bond as we move down the group. Next are the group 18 elements. Noble gases are chemically inert towards hydrogen because of their stable electronic configuration. Chemically inert means they are not chemically reactive. Next topic is reactivity towards oxygen. Group 16 elements form oxides of the type EO2 and EO3, where E is oxygen, sulfur, selenium, tellurium, and polonium. First, we will study the EO2 type of oxides. Ozone, which is having the formula O3, sulfur dioxide, which is having the formula SO2, are gases, while selenium dioxide with the formula SeO2 is solid. These oxides are acidic in nature and they react with water to form acids. First reaction is sulfur dioxide reacting with water to form sulfurous acid. The second reaction is selenium dioxide reacting with water to form selenious acid. The reducing property of dioxides reduces as we move down from SO2 to TeO2. So, sulfur dioxide is a reducing agent while TeO2, that is tellurium oxide, behave as an oxidizing agent. The other type is the EO3 type of oxides. SO3, SeO3, TeO3 are also acidic in nature. They dissolve in water to form acids. Selenium trioxide reacts with water to form selenic acid. TeO3 reacts with water to form telluric acid. Now we move on to group 17 elements. Elements of group 17 forms oxides with oxygen, but most of them are unstable. Fluorine forms 2 oxide, OF2, that is oxygen difluoride, and O2F2, that is dioxygen difluoride. Out of the 2 oxides, only oxygen difluoride is thermally stable at the temperature 298 Kelvin. Both the oxides are strong fluorinating agents. Fluorinating agents are electron deficient fluorine atom which serve as reaction active species. O2F2, that is dioxygen difluoride, is used to oxidize plutonium to PuF6, and this reaction is used to remove plutonium from the spent nuclear fuel. Chlorine oxides like Cl2O, ClO2, Cl2O6, Cl2O7 are highly reactive oxidizing agents and they tend to explode. ClO2, that is chlorine dioxide, is used as a bleaching agent for paper pulp, textiles, and water treatment. Bleaching is a process of destroying the natural color. Bleaching is used in paper industry to whiten the pulp. Bromine oxides like Br2O, BrO2, BrO3, they are the least stable halogen oxides. However, they act as powerful oxidizing agents. Oxidizing agents means they can accept electrons. Iodine oxides like I2O4, I2O5 and I2O7 are insoluble solids, but they decompose when heat is applied. I2O5, that is iodine pentoxide, is a very good oxidizing agent and is used for the estimation of carbon monoxide. Hence, it is observed that the higher oxides of halogens are more stable when compared to the lower ones. Next are group 18 elements. We know that group 18 elements are chemically inert, hence they are not reactive towards oxygen. Next topic is reactivity towards halogens. So again we will follow the same order, that is first we will study group 16 elements, then 17 and then 18 elements. So first are group 16 elements. Elements of group 16 react with halogen to form large number of halides like EX6, EX4 and EX2, where E is sulfur, selenium and tellurium. First we shall study the hexahalides. Hexa stands for 6. Examples of hexahalides are SF6, SeF6 and TeF6, that is sulfur hexafluoride, selenium hexafluoride and tellurium hexafluoride. These are colorless gases. They have sp3d2 hybridization and have an octahedral structure. Sulfur hexafluoride is exceptionally stable due to steric reasons. Steric means the spatial arrangement of atoms in a molecules which affects the chemical reaction. The stability of halides decreases in the following order, starting from fluorides, chlorides, bromides and iodides. Next are the tetrahalides. Examples of tetrahalides are SF4, that is sulfur tetrafluoride, SeF4, that is selenium tetrafluoride, TeF4, that is tellurium tetrafluoride, and TeCl4, that is tellurium tetrachloride. The tetrahalides have sp3 hybridization and trigonal bipyramidal geometry. Also one equatorial position which is occupied by the lone pair. Next are the dihalides. Examples of dihalides are SCl2, that is sulfur dichloride, SeCl2, that is selenium dichloride, and TeCl2, that is tellurium dichloride. These dihalides exhibit sp3 hybridization and have tetrahedral structure. They possess two equatorial positions which are occupied by the lone pairs. Next are monohalides. Monohalides are dimeric in nature. Dimeric is an oligomer where two monomers are joined by the bonds which can be strong or weak, covalent or intermolecular. Oligomer means a molecule which contains same repeating units. Examples of monohalides are S2F2, that is disulfur difluoride, S2Cl2, that is disulfur dichloride, Se2Cl2, that is diselenium dichloride, and SeBr2, that is selenium bromide. These dimeric halides undergo disproportionation. Here is an example of the same. Disproportionation is a reaction in which a substance is simultaneously oxidized and reduced, giving two different products. Next are group 17 elements. We already know group 17 elements are called as the halogen group. So these halogens combine among themselves to form a large number of compounds which are called as interhalogen compounds. So they could be of the type XX-, XX3-, XX5-, and XX7-. Here X is the halogen with a larger size and X- is the halogen atom with a smaller size. Next are group 18 elements. We know that group 18 elements, which are also called as the noble gases, are chemically inert, which means they are not chemically reactive. However, krypton and xenon directly react with fluorine to form fluorides. Here is the reaction. Xenon reacts with fluorine to form xenon difluoride. Xenon fluorides like ZeF2, that is xenon difluoride, ZeF4, that is xenon tetrafluoride, and ZeF6, that is xenon hexafluoride, are all crystalline in nature, which sublime readily at 298 Kelvin. Sublime means it gets converted from solid to gaseous state without undergoing the liquid state. They are fluorinating agents as well. The next concept is reactivity towards metals. Elements of group 16 react with metals to form compounds. Some examples are as follows. The first reaction is aluminium reacts with oxygen to form aluminium oxide. Second reaction is copper reacts with sulfur to form copper sulfide. Third reaction is magnesium reacting with selenium to form magnesium selenide. Next are group 17 elements. Group 17 elements also react with metals to form metal halides. Some examples are sodium reacts with chlorine to form sodium chloride. Magnesium reacts with bromine to form magnesium bromide. The ionic character of the metal halides decreases in the following order. Here, M is the monovalent metal. Monovalent means it has only one valency. Metal halides having metals in their higher oxidation state are more covalent than metals in lower oxidation state. For example, SnCl4, that is tin tetrachloride, is more covalent than SnCl2, that is stannous chloride. PbCl4, that is lead tetrachloride, is more covalent than PbCl2, that is lead chloride. Covalent means they can share pair of electrons between atoms. Next, we move on to group 18 elements. Group 18 elements, which are also called as the noble gases, are chemically inert and they do not react with metals.